Welcome. Today we're going to talk about designing databases. And a database is a shared structure that stores a collection of end user data, which are facts that are of interest to a user or a company, and metadata, and that's the data about the data. For example, what's the data type that is being stored for each field? How is it organized into tables? Things of that nature. It describes the data characteristics and relationships. Now, databases are stored in database management systems. And these are collections of programs that manage the database structure, control access to the data stored in a database. They act as an intermediary between the user and the database itself. Databases, there's multiple databases in a DBMS. So the DBMS enables data to be shared, and it presents the end user with an integrated view of the data. It'll receive and translate application requests, and we can write applications to access the data as well as have users access it directly. And it'll translate those application requests into operations that are going to fulfill the information needs. A DBMS hides the database's internal complexity from the application programmers and users. Now, database design focuses on the design of the database structure that will be used to store and manage end user data. A well-designed database facilitates data management. It generates accurate and valuable information. On the other hand, a poorly designed database causes difficult to trace errors. So we're going to look at databases, database management systems, and the relational database model. This is the most popular model. It's been around for 40 years and has stood the test of time. So, a relational database model enables logical representation of the data and its relationship. It's facilitated by the creation of data relationships between tables where we store data. And it has a logical simplicity that yields simple and effective database designs. Data modeling is an iterative and progressive process of creating a specific data model for a predetermined domain of data needs. We have some need for data storage, and data modeling is this process we go through to create a data model. A data model is a simple representation of these complex real-world structures, and it's useful for supporting the actual database we're creating. So a model is an abstraction of a real-world object or event. Now, data models are important because we can use them as a communication tool with the users, so we understand what is their need, and we make sure we're understanding it correctly. It gives an overall view of the database. It helps us organize data for different user groups. And it's an abstraction that we can use for a good database implementation. The relational model is based on tables. So we organize our data into tables, which are two-dimensional structures. They have columns which represent attributes or fields. These are characteristics about a particular entity. A table, one table is about one theme or entity. For example, instructor might be an entity or theme we're interested in. Student might be another entity or theme that we're interested in. So that's the entity, that's a table. The table will have characteristics. So an instructor, we might be interested in the instructor's name, the department they're in, the salary they get, things of that nature. So attributes are characteristics that we want to track for a particular entity. Rows are the entities themselves. So John Smith would, as an instructor, would be a row, and we would have a name, a field for that row. John Smith would be in there. Department, let's say they're in the College of Business, that would be in there. And salary, let's say it's $100, that would be in there. So the relational data model is about tables where we store data characteristics about entities we're interested in, and then relationships between those entities. So an entity relationship diagram, an ERD, is a graphical representation of entities and their relationships in a database structure. So an entity is a unique and distinct object that we are collecting and storing data about. An attribute is a characteristic of that entity. And a relationship describes an association between the entities. So for example, we might have a table or an entity called department and another table or entity called instructor. And an instructor might belong to only one department. So for example, I am only in the College of Business, that department. On the other hand, a department may have many instructors in it. So this is the idea of a relationship. There is some sort of association between the entities. What I just described was a one-to-many. Now, let's take another relationship, one between students and classes. Well, one student may take many classes. On the other hand, one class may have many students. So that is a different type of relationship. It's a many-to-many relationship. So we have different types of relationships that we deal with. Now, attributes are characteristics of entities. A required attribute is one that has, we must have a value for. We cannot leave it empty. An optional attribute is a field that's there, but it can be left empty. Attributes have domains, which is a set of possible values. So for example, an instructor's salary would be an integer domain, and we might restrict it further and say it has to be an integer between 20,000 and 100,000. We wouldn't put text in as the domain for a instructor salary. Text would be more appropriate as the domain for the instructor's name. Now, in order to get to a particular record, we need an identifier. And an identifier, is also known as a key, is one or more attributes that uniquely identify each entity instance. So here we see an example of some entities: customer, order, item, distributor. These are big picture things that we're interested in. And then the things we want to track about each one of those are called attributes. So for an order, we want to know the order number. We want to know the customer number of the customer that the order was for, the order date, and when the order was filled, things of that nature. So there's several types of attributes. A multi-valued attribute is an attribute that can have many values, and several. A derived attribute is one whose value is calculated from other attributes. So a multi-valued attribute might be something like a phone number. A person's phone number attribute, they may have a cell phone, a work phone, or a home phone. Now, for a student or an instructor, we might have their date of birth as a field, and then we might also have age. Well, age would be a derived attribute because we're deriving age based on another field, which is their date of birth. So a simple attribute is an attribute that cannot be subdivided. And a composite attribute is one that can be subdivided. So let's take, for example, an address field. Well, an address field can actually be subdivided into things such as street, city, state, and zip code. So an address field is a composite attribute. City, state, zip code are simple attributes. Address can be subdivided into other parts that logically make sense, whereas a city, a state, and a zip code cannot be subdivided into other parts that logically make sense. A single valued attribute is an attribute that has only a single value, and a multi valued attribute is an attribute that is made up of many values. Here we see a diagram of a composite attribute, an address that is composed of a street, city, state, and zip code. A single valued attribute has only a single value. So a customer entity only allows one telephone number for each customer. We're not going to allow multiple phone numbers. If a customer has more than one phone number, then if we have a single valued attribute, we can't put it in that particular table. A multi-valued attribute means the potential for containing more than one attribute at a time. So if we had a customer and they had 3 phone numbers, we could put those 3 values in that field. Relational databases do not allow multi-valued attributes. And that is because in the past, those caused problems. So the way they handle it is you create another table of phones, and then you relate a record in your customer table to their phone numbers in the phones table. And again, this is the convention in the relational database system. And they did it because they were addressing a series of problems in the 60s and early 70s with databases. and they implemented these rules to simplify things and to therefore have more reliable databases. Today, NoSQL databases have relaxed some of those rules, so they do allow multi-valued attributes. Relational databases do not. So again, a stored attribute might be something like date of birth. Age is what we derive from another attribute. So if we take today's date and subtract that from that, their date of birth, we could get the person's age. So we could derive the age without storing it as a separate field. And usually we don't store a derived attribute because it will become stale. If we put in a person's age at the time we create their record, they might be 35. 10 years later, unless we update that field, it still says 35. So we don't like derived attributes for that reason. A null value means we just don't put anything in there. And it may be because for this particular record, the field doesn't have a value, or we just don't happen to know it at the time we're entering the record. So we will put in a no value, and that's called a null. So there's two common ways of documenting entity relationship diagrams. The Chen method, and Chen uses rectangles to represent entities and ovals to represent attributes. James Martin developed what's known as information engineering, and he uses a more tabular approach. So here's the Chen model with attributes, and that's the one we'll be using here. So relationships. A relationship is an association between entities, and relationships are always in two directions. So student and classes, we have an association. A student will take classes, and a class will have students in them. Participants are entities that participate in a relationship. Cardinality expresses the minimum and maximum number of entity occurrences associated with one occurrence of a related entity. So we can say, for example, with a department to instructor relationship, an instructor has one department that they belong to, whereas a department will have many instructors that are part of it. Likewise, student and classes, that's a many to many. And so we've got a student that can take many classes and a class that can have many students. So cardinality, again, expresses the number of entities that to which another entity can be associated in a relationship. And again, it can be one-to-one, one-to-many, and many-to-many. Now, Chen, as I mentioned, uses rectangles for entities. The Chen notation uses a diamond for representing a relationship. And we see that here, a customer has orders. And so we have a diamond called has. That's the relationship between customer and order. Now, a one-to-one relationship is such that entity A can only be related to one instance of entity B, and entity B can only be related to one instance of entity A. So, for example, an employee that manages a store, you'll have one manager. So that relationship has one employee that manages one store. We could likewise, in our college example that I was giving before, say dean and department. So dean would be an instructor, but the dean in the dean relationship, there's one employee that is the dean that manages the department. So it's a one-to-one relationship. A one-to-many is where one entity can have a relationship and have many records in the other table. So a customer record, one particular customer may have made many orders. So one customer will have many orders, but an order is only for one customer. So that's a one-to-many relationship. And then a many-to-many relationship. Again, you can have many records in the first table related to many, one record in the first table can be related to many records in the second. And in the second table, one record in that second table can be related to many in the first. And again, let's go back to students and classes. So students is our first table. One student can have many classes. Going to the second table, classes, one class can likewise have many students. So that's known as a many-to-many relationship. So we can also have weak or non-identifying relationships. And that's where a particular table does not have its own primary key, but it uses the primary key of another table. And remember, a primary key is something that uniquely identifies a particular row in a table or record in a table. So a classic example is orders and order items. So an order is going to be composed of several products that you want to purchase. So when you go on to Amazon, for example, your cart is an order form, and you might have several items in your cart. So those items are going to be related to the order. So they will take the order key, in other words, the identifier for that order. And you know, when you click and you pay and you get all that, it'll give you the order number. Well, those items have that same order number, and then they'll have a sequence. Item 01, item 02, item 03. So the items have taken the primary key of the entity they're part of, in this case an order, and they add a sequence to it. A strong relationship is one like order. It has its own primary key, so it doesn't need. It's not relying on something else to give it its key. So with a many-to-many relationship, it turns out relational databases cannot implement a many-to-many relationship. They can implement one-to-one or one-to-many. So what we do is we take a many-to-many relationship and we implement it as two one-to-many relationships. And we do that by creating a table in between the two others, the two tables that are in question. So for example, we might have a many-to-many relationship between students and classes, and we have a registration table that we then put in place so that we've got that registration table is going to then be composed of relevant information from the student side and relevant information from the class side. So that's what it means when it says many-to-many relationships have to be replaced with a collection of one-to-many relationships. Okay, another thing that relational databases are not good at and they can't implement are composite or multi-valued attributes. So the way we handle multi-valued attributes is we take that multi-valued attribute and we make it a separate table and we give it the primary key from the table we're taking it from. So for example, let's say customer, and we've got a field in the customer table called phones. And we want to be able to have multiple phones, things like cell, work, home, etc. So we can't put 3 values in a relational table. That's against the rules. So what we do is we create a separate table called phones. And then we take the customer ID from the customer table and we put that over as the ID for a record in the phones table. And then we join that with the phone numbers. So let's say my customer number was 123 and I had 3 different phone numbers. Well, we'd create a record for me in the customer table, 123, and give my other information. Then we'd also create a record in the phone table. And we'd put customer number, we put 123, my customer number. And then the phone number would be the other part of that table. And then we'd have my 3 or 4, how many phone numbers I want to put in there as the other field. So that's how we handle multi-valued. A composite, we just separate the fields logically. Address would be separated into street, city, state, and zip. And then we put those simple attributes into our table. And here's a graphic of a composite entity. Again, there's a couple of ways of designating cardinalities. You can have, like on the top, 1 to M. To me, that's the cleanest and simplest. But sometimes they use notations like we see below. This one is 1 and it must have 1. It can be associated with 0 to many orders. Okay, so once we've got our entity relationship diagram, we've identified the entities that we're interested in, the attributes they have. We've looked at the relationships between the entities, like students take classes, instructors belong to departments, and we've identified the relationships. Then we can take that relationship and transfer it over to a set of tables in our relational database. So entities and relationships can be represented as tables in the database. So for each entity we have and each relationship, we can make those into a unique table in the database. So again, entity is used synonymously with the word table. Table is what we are looking at in an actual functioning database. An entity is more what we have in our diagram when we're trying to figure out how to organize our data so that it makes sense logically to both us and to the customers. So here's a customer table. And we have the customer attributes, the number, the first, last name, and phone number. When we have some tables that we're going to have a relationship between, so for example, customer and order, and sometimes we'll want to get customer information by itself. Other times we're going to want to get customer information and then all the orders that they have made. Well, we're probably going to have a field called customer number in our customer table, and we're likewise going to have a field called customer number in our order table. So when we do an operation for both customer and order together, for example, we want to get the customer information and then all the orders they've had, we're going to have this name, customer number, that's the same in both tables. So in order to handle that, we have to qualify the name of that attribute with the name of the table. And that way the database will know, okay, well, they're talking about the customer number as opposed to the order customer number. So again, an entity is represented as a set of attributes, and these are properties possessed by all members of that entity. So for example, instructor, we might have, that's the entity. We might have the attributes for the instructor, their ID, their name, their street, their city, their salary. A course might be an entity. The course ID, the title, the credit hours might be attributes we track about a course. The domain is the set of allowed values. So domain for salary might be an integer between 20,000 and 100,000. Now we can have different attribute types. We've talked about simple and composite, single valued and multi-valued, and derived. This is on our entity relationship diagram. And of course, we would have to handle those as we talked about a couple of minutes ago, when we translate them into actual database tables so that we can store our data in an actual object, not just have a picture of it. One important part of this whole concept is the idea of keys. And a key consists of one or more attributes, and this set of attributes uniquely identifies each row in a table. We need to be able to go to my specific customer record. So I have to have an identifier that lets us do that. That identifier that lets us go directly to my record is a key. The key might be, a customer number that is assigned to me. It's not going to be my name because there might be another George Ray in the customer database. And so we would not be able to go to one specific record. Amazon, if it used the customer name as the key, and so I type in George Ray, it's going to probably pull up hundreds of records, customer records with the same name. So the idea of a key is it's an attribute or combination of attributes that uniquely identifies any given row. Okay, so if we have a key, then we can get any specific information we want. What we have to do is we have to designate the table the information is in. So let's say that we're interested in the customer address of George Ray. So we're going to have to name the table, customer table. We're going to have to name the column, the address column. And then we're going to have to give the primary key. Okay, primary key for George Ray is 123. So with those three pieces of information, we can retrieve my address, 109B Whitehall, and give that to the interested party. So a primary key has a couple of characteristics. One, it should be something that never changes. And it should also be something that would not be blank or null. And so here's some examples of logically relating tables by keys. So we have a customer table, we have an order table, and we have customer number. And so the customer number is associated with the order.customer number. The primary key is the customer number. The order.customer number is our foreign key. And we see that the primary key in this case points to two orders that I've made. So this is a one-to-many relationship. So a foreign key is a primary key of an entity that is used in another relationship to identify instances that are related to that particular record. So the foreign key here relates orders that are related to my customer number. Let's say I'm customer number 1111, and then these are the order numbers related to my customer record. And a join operation is when we join two tables together, customer and order, so that we can find more information that is stored in either one of them. So by joining customer and order together, I can get all the customer information along with each order a customer has made and all of the customer information. So we join those things together by getting a key and associating it with getting a primary key and associating it with a foreign key. So we would join customer and order on the keys customer number, customer.customer number, and order.customer number. Also, one thing to keep in mind is a table or entity can have a relationship with itself. So, for example, courses might have prerequisites. So a prerequisite would be an entity, and it would use course number as its primary key. And then you'd have other course numbers that are prerequisite courses to it. That's a relationship between the course table and itself. So foreign keys don't necessarily need to reference a primary key in a different table. They can reference a primary key in the same table if it's a relationship with itself. Okay. Any questions on that?